Yeah.
Is it possible to interpret it using eigenvalues and the region of stability?
Of course, it is possible to use eigenvalues. So what is the matrix going to be like if you have, let's say, the upwinding if u is greater than 0? Right, so the upwinding, so let me write it down. Here, upwinding for u greater than 0. So the matrix would be what? I would be, so du dt of 1 is equal to u1 minus un. So in terms of the matrix, the first row would be what? Right, u1 minus un. What is the first row of the matrix? Yeah, so I get 1, a bunch of zeros, and minus 1, right? And the second would be 1 minus 1. So I get a 1s on the diagonal and minus 1s on the subdiagonal plus this corner entry. So let me see. I have a matrix A is equal to identity of, let's say, 100 minus row, is it row, not row, circ shift, yeah. I think in Python it's row. Is it, I think I'm shifting down, so it's 1. So let's see. I'm getting the correct matrix A. Yes, I'm getting the correct matrix A. So let me just plot the Eig of A as dots. Did I? Let me close this guy. Here is what I get. Okay. Of course, the real real eigenvalues would be this particular A divided by delta x, then multiplied by minus u, right? So after divided by delta x, of course the circle gets blown up by a factor of 100 in this case, right? Because 1 over delta x is 100. And then times minus u, which means the whole spectrum of eigenvalues is going to be rotated for 180 degrees, because this is complex space, right? Putting a minus is rotating the whole thing by 180 degrees. And then you need to multiply, and also times 10, u is equal to 10, right? So it's also blown up again by a factor of 10. And then you need to multiply by your delta t, so that the whole circle is small enough to fit into the stability region of the integrator, right? So in this case, your delta t is probably going to be on the order of 1,000th for most explicit schemes to work. All right. Okay. But another thing is that if u is positive, if u is negative in this case, then the eigenvalues actually lies on the right side of the complex plane, right? So anything other than a very good, like backward Euler, a very stable implicit integration scheme with a big delta t would not work if you choose the wrong direction to upward. Okay. Questions on this? No? You look confused.
I'm getting there.
Okay. Yeah, so basically, if you have eigenvalues on the right side of the plane, that means even if you integrate the ODEs exactly, you will blow up. Yeah. So that usually means a bad discretization of the PDE. Actually, you actually want to make sure like every single eigenvalue lies either on the imaginary axis or on the left plane. Otherwise you should fix your spatial discretization. All right. I mean, usually the more difficult cases are not like this obvious. It's usually just a maybe your boundary condition is not implemented properly, and you get just one or two eigenvalues on the right hand side of the plane, and you can almost see it from how the solution blows up. Just to look at where the solution starts to have troubles, and if it's a boundary condition related issue, it's usually starting to blow up from that boundary. Okay.